Hello everyone, this is Josh Gazero reporting in. I'm going to be doing a quick demonstration of our camera calibration module. It basically uses our LEGO cameras and it rectifies images based on how it's perceived through our calibration procedure. For more information, you can go to our website www.riskproject.com/seniorproject /senior_project. Go to the software. When you can go to the software design section. You can create your own login. Once you go there, you can look under our final. We have initial and final project software system design. Just click on under final design. You can click on the camera calibration rectification page, and it gives you more information. One thing I want to note is that on the page it gives the reason why we decided to make it. The first reason was we wanted to make our system more robust for other people to use on their own two cameras at home. And the second reason was that we realized that our cameras were slightly uneven and that one was a little bit higher than the other. So we implemented our camera calibration technique using MATLAB code and a few resources we found online. So without further ado, let's walk through a few steps that we used when calibrating images that we take using our LEGO cameras. So here we have our sets of images using templates that we took in the robotics lab. As you can see, there's James Gedney holding our checkerboard template. This is what we used for our calibration procedure. Next we read our images into our workspace. The images are entitled Old Left, and they're JPEGs, and so Old Left JPEGs. And then it reads the three images into our workspace, as you can see. Next, we're going to extract our grid corners. We leave a few of the defaults, like 5 for allowing the window size to be 11 by 11, and then we're going to not do the automatic detection. And we're going to click on it asks you to click on the 4 extreme points in order to automatically detect the corners. And so we detect our corners for our image. Next, we need to input the size of each square, which are already pre-measured as 30 millimeters each. And then by doing this, it automatically detects our corners, as you can see. Corners. And in this way, we have our corner extraction for each of the 3 images. So let's do the next one. Making sure always that the images come out okay and that the corners are fairly accurate. Looks good. Let's finish it with our last one. And in case you're wondering the reason why the calibration object is held at different angles, is because it gives us better range for predicting our calibration for our cameras. And you can add distortion if the image is slightly distorted, but we don't need that. And we can do it better by reprojecting the corners on the images, but for a simple example, I'm not going to do that. The next step is we're going to run our calibration procedure. The calibration procedure uses 2 steps. The first is initialization, and then the next one is a non-linear optimization process. As you can see, it outputs the calibration parameters after initialization, the focal length, the principal point, skew, and distortion. And after it, then it runs the nonlinear optimization. Basically what this is just it uses iterative gradient descent, and it uses a closed form computational of the Jacobian matrix. And as we can see, it uses 16 iterations, descent iterations, and after the optimization, it outputs uncertainty for each of the focal length, principal point, skew, and distortion. And this is for one camera. This is enough for us to be able to calibrate one of the cameras. But since we need both cameras, we need to do the same thing for the right pairs of images. And so I went ahead actually to save time, and I did the right pairs of images ahead of time. So what we're going to do is we're going to save our calibration results right here. It pops up in our folder, and we're going to relabel them calib results left.mat. This is a data set, and then we also have our right data set, left and right. So our next step is we're going to run our stereo vision very quickly. we're gonna combine these two data sets and then we're gonna calibrate them. Calib results left.mat calib results right.mat. So we see our two sets of images, and what we're going to do is we're going to run a stereo calibration, which further uses only 8 descent iterations and gives us greater accuracy with less uncertainty between the two cameras. And now we can take a look at our two extrinsic points combined, and we see a nice view of how our LEGO cameras look in relation to the two data sets, 3 data sets combined together. So it gives us a nice picture, and we can later use this to estimate the distance between the camera and the checkerboards, which I'll show you in another extension of our project. And we can also use these intrinsic parameters for left and right camera to more accurately predict the border that needs to be cut. See this in the picture, which we rectify calibration images. We can have perfect epipolar lines between the two images, despite being offset in cameras being next to each other, because obviously the LEGO cameras have a great degree of error when it comes to taking accurate stereo pictures. And so we can take a look at the output that was spit out after we rectified our images, and going through we see that there is a great amount cut out for our left image. Our right image is used as a reference, but our left image is what is adjusted in order to make our lines epipolar. And when I say epipolar, you can take a look at the website. You can see matching what epipolar lines are the lines, parallel lines that match points in two different images. So you have a left and right image, right? And so using belief propagation, we can match points on the same image. Even though it's taking a picture of the same thing, it's clearly the same thing. There should be all the points, but only certain points can be matched, because one, of the quality of the picture, and two, because they're taken at different angles. And so we have our match points, but as you can see, the epipolar lines are very strongly sloped. However, after our rectification, we see the epipolar lines are clearly parallel. After you see the border and the offset of each picture was taken into account. And the right is only taken a little bit off right here in the bottom. It's used as our reference. So that's pretty much it for our rectification and calibration toolbox. For more information, let me know. Thank you very much, and please enjoy the rest of the presentation.